So now we are going to learn about the different models in the stereochemistry, like Cram's model, Felkin and models. So when we are going to consider about the diastereoselectivity in a particular organic compounds, so we are going to learn about the concept of the dynamic stereo, because the diastereoselective compounds, we all know what the diastereoselective compounds are. So when the diastereoselectivity, for example SR, R can be converted into R, S and S. So in the diastereoselectivity, when we have different compounds of organic scaffolds, we will see about the concept of dynamic stereo, and in that particular scenario there are two models on which we have to work: Cram's model and Felkin models. So, and there is another, that is the Chelation model. So in the detailed system I am going to explain you about different types of the model. So first of all we will do about the Felkin model. So Felkin model, it's a very important model in the organic chemistry. So what you have to do is you have to start numbering. This is the carbonyl group and this is the first, second and third. So the third carbon after the carbonyl group is there. So when we are going to add a particular reagent, it's an organic chemistry reagent, you should learn the different functions as well as the you can learn the different names of different functions, different reactants, so that you can use a specific reagent for a particular product. So when we're talking about the Felkin model, like we have a particular reactant, and on that reactant we have a reagent, that is a methyl magnesium bromide. This is a very good example of the Grignard reagent. So what the function of the Grignard reagent is that the particular carbonyl group get reduced and the attachment of OH and the R group is there. So what we are going to do is like I am saying this particular C double bond OH, that this particular group is far away from this particular asymmetric group. So in this reaction, the phenyl group, either it can be a hydrogen, it can be a methyl group, is very far from the carbonyl group. So in such products, we are going to get the racemic products. In such reactions, we are going to get the racemic products. So why we are going to get the racemic products? Because here the carbonyl group, that is the C double bond H, is very far away from the asymmetric center, that is it's far away from pH, H, or we can say we can have a methyl group as well. So from that they have a very good distance. So that's why we are going to prioritize the Cl bond instead of odd bonds. So what we have to do is we should only have to learn the work of the reagent, as well as we have to check either on the reactant our reagent is going to react in which manner, either in an anisotropic manner or in a diastereotropic manner. So you should have a very good knowledge of the planes as well as about the topicity, like the plane on which the nucleophile, or we can say that reagents going to attack the particular phase, either it can be a pi phase or it can be a homo phase. So that particular phase should be in such a way that our product that we are forming through our approach should be right. So in the particular stereochemistry we have to build our own approach. In stereochemistry we have to build our own approach. For that scenario I am going to teach you about different Felkin model, anti-Cram's model and Chelation models. So in the reaction, the particular C double bond OH is very far away from this particular compound, because it can be 1, 2 and on the third position it is. So that particular distance is responsible for the formation of the racemic products. So in this particular reaction we are getting the racemic products. And the products are this. So in this particular reaction we are going to get the racemic products, because we are not getting a specific product having a specific stereochemistry, because in such a case when we have a carbonyl group that is far away from the center, so that's responsible for the racemic mixture. So in this particular scenario we have a 50% chance that our product is this and 50% this. So when they both combine, it can be a racemic mixture, and the racemic mixtures are overall optically inactive because the R will cancels S. So that's why the racemic mixtures are come under the category of optical inactivity. So this is the final product. So this is the final product of that reaction. Final product of every reaction is very important. In this, like, you should know what's the final product of the reaction, either this or this. So you should know about the final product, only then you can able to learn about the different reagents and reactants. Now consider another example or a very important question. In the asymmetric center, when we have a carbonyl group, just adjacent we have a asymmetric center. This is our carbonyl group. We'll call this particular group as carbonyl group. Carbonyl group or carbonyl carbon, you can call this group as this. And when this particular carbonyl group is attached adjacent to the asymmetric center, we have a pH which is attached. We should have a pH, H or Me. It means that we have a phenyl, we have hydrogen, or we can have the methyl group. More the bulky group are in the very close proximity of the carbonyl group because they are very close to each other, because this particular asymmetric center and this particular carbonyl group are very close to each other. And when these things are very close to each other, in the product we are going to get the diastereomers. The reagent is same. See, the reagent is same, but our reaction changes, our reactant changes, so our product will also change. So in the product, what we have, like in the product, we are going to get the diastereomers, because here we can have a phenyl, hydrogen or methyl, and we are going to get the diastereomers only when the bulky substituents are in the very close proximity of the carbonyl group. So phenyl is a bulky substituent and it's in a very close proximity of the reactant, because this is a reactant. Now, so we use the Felkin model, or we can use the Chelation model. So from these two models we can use one. Either we can use the Felkin model or we can choose the Chelation model. Now, so we are going to learn this particular Felkin model stepwise. First of all, you should see the reactant. Like either the particular model will able to apply or not. You have to see the achievability of the study first of all. So either the study which we are doing in the particular reaction, every reaction has its own study. So we have to see like a particular reaction should be achievable in the given duration of time. So when we have a particular reaction, we have a reagent, that is the sodium borohydrate, and we have a reactant. So sodium borohydrate is a hydride reagent which is usually responsible for the reduction purposes. So what the first step for a Felkin model is, you have to convert the reactant to Newman projection. So you have a reactant, and from that you have to convert your reactant into the Newman projection. It's very easy to convert, but it's sometimes because complicated if you are just marking or guessing the answer. So first of all, you have to convert your reactant into Newman projection. It's compulsory. Just consider it compulsory and solve the reactant into Newman projection. So when you are going to do that, what you have to do is, you have to put the carbon group. So in this we have a double bond O and MEH. We have double bond O and Me. So what we are going to do is, we are going to do like this. So when we have a circle, it's we have two carbons. So a carbon which is connected with Me. Why I have drawn the structure like this? Because C double bond or Me. So C double bond is above the plane and Me is just opposite to the C double bond O criteria, and we have this particular group. And when we are going to see the structure in such a way, like C double bond O and Me comes in front of me. C double bond O and Me comes in front of me. So we have to check the directions of pH, H and Me like this.